Okay, hi everyone. My name is Kevin. I'm going to give a talk about estimating the weight of the car from their dimensions. So a little about me. I was doing PhD in particle physics, and well, it's just a title, but basically what I did is basically doing stuff like C++ and Pythons, and doing data analysis. And I joined Atlas collaboration at CERN's and contribute to the CI/CD in the Atlas Trigger software. And yeah, my day-to-day life is basically uh, building the data pipeline and then write the analysis codes and then debugging as well. And I'm open to work. So maybe you wonder what is the talk about from the title? Is it physics or is it engineering? No, it's supervised learning because we can do the actual weight measurement from the car dimensions. Let's say from the we know the density of the materials of the cars, but there are many of material. But the car is consists of many materials, and they have different densities and they have different weight distribution as well. So it's gonna give a edge. So let's just fit everything into the supervised machine learning. And this is the repository. You can get the code here, and yeah, basically the data was taken from this websites in opencanada.ca, and this is the feature. So we have this overall length, overall width, overall height, front end length, etc., etc. And the target is the curve weight in this data. And here we can see, for example, in this is the manual of this data. So you can just open this page and then find out this in this manual they are basically have this kind of abbreviation and it's not really meaningful. So in my code I just put the actual naming. For example, this overlaying is oil. And so basically what I did is I was doing I was comparing with three models. For the first is scikit with a random forest method, and then also with TensorFlow and PyTorch, and both of them are neural networks. So for the neural network, the feature and target I scale it with the standard scaler from Sklearn. And then the best model so far is here we have the first neuron. The first neuron is 256, and then second layer is 128, and then 64, and then finally the final results. And yeah, I play around with these neurons, and I found this is the best configuration so far. And here we have the activation function of a rectifier linear unit and optimizer with and Adam optimizer, and loss function is a mean square error. And here is the plot for example, PyTorch. So here is the plot for the loss over iteration. So here there is some kind of spikes over here and there. And this is because, this is iteration, not epoch. So every time the new epoch begin, there is some spikes and then finally it converges and then so on and so on. And this is the plot for the comparisons between the models for the actual and predicted. And ideally it should be y equal x. And here we can see it for PyTorch and TensorFlow. They have wider distributions, despite the R score is higher than, for example, the PyTorch. It is higher than, for example, the random forest method from Sklearns. And here I use the mean absolute percentage error instead of the mean error square, because for example, if we have this because the weight of the car is like 1,000 kilograms, and if the difference is, like, say, for example, 10%, it's going to be something like 100 kilogram already, and we supply it to the mean square error and it blow up to like 10,000 or something. So it's not for the unscaled weight, it's not a good indicator to check whether the prediction is correct or not. So using this MAPE instead. And yeah, any question for the presentation?
Is there a particular reason you have this thing on the right hand side?
You mean this table?
I can take the mic and ask. There are some like observations at like 4,200, and like for all the models, you have some weird observations there.
Yeah, I see.
What's
I
up?
see. So yeah, so in the data we see that outlier here because there is one is very big, maybe it's some kind of truck or something else, and there is also on the very small end there is also something doesn't match. So I think it is some kind of an outlier. I don't know, maybe it's a mini wagon or something. But overall, yeah, it's almost centered in the y equal x.
You can take it.
I just wonder if you consider only gas propulsion cars or electric cars, and how do you if you see differences between?
Yeah, basically, I don't differentiate anything. So this is just we have the car data, and I don't differentiate whether this is with a fossil fuel or electric cars.
But you have a mix of both.
Yeah, this is the mix of both of them, but more or less in the end, they have the similar distribution.
Okay.